Okay, thanks for joining everyone. I'm Tim McDonald, Chief Scientist of Electromagnetic Applications. Today we're going to talk about some new tricks and a few old tricks to help make practical work for electromagnetic effects, E3 and EMC, a little bit easier. So myself and my colleagues listed here, we work often as consultants on EMC and E3 programs around the world. So over the years, we've developed some working procedures and have some new technologies that help make some of those practices a little easier. So I'm going to talk about this. The point of the EMA webinar series is to be informative. So we're here to let you know about what we do in our workflow. Of course, this can be applied on using many different tools and many different platforms. And again, I want to thank everyone for taking time out of their busy schedule to attend this webinar. And I think it's going to be worth your time because you'll see some things that are now automated and some new technical approaches that are really, it feels like magic to me when I see them, and not because you know, we're pulling something out of a hat, but because I know the pain and the amount of work we had to go through before some of these procedures were developed. So everything here is a set of tools that I think form a reasonably complete toolbox for what people might want to use on an E3 or an EMC program. And I think when you see them too, you're going to say, that saves a lot of hassle. So again, our intended audience here is EMC, E3 people, and also people who are, I guess, learning or EMC curious. We're going to be taking questions as we go along, so please use the Q&A box. My colleagues Jennifer Kidegorski and Eric Miller are going to be collecting those questions. We'll answer at the end. They may answer some of them via directly by chat, so feel free to jump on the chat box, jump on the Q&A especially, and give us questions as we go along. And my email address is here. If you have any questions about this, you want to know how you can add one or more of these components into your workflow, or you just have a general question, feel free to send that my way. That's what we're here for. Okay, so who are we? EMA, we're in Denver. This is the EMA building. We are PhD and a few master's levels EM analysts. We do computational software development. We do EM measurements. But mostly we work as consultants in EMC and E3 programs. So sometimes that means we're badged at companies around the world doing EMC and E3. Sometimes we're supporting those teams, helping build tools for them and fill in gaps whenever they need help. And we're in Lakewood, but we can go anywhere to do the work that we do. And an important partner here is IDS. So IDS is this is their Pisa office in Italy. They have over 500 employees. They're almost as old as EMA. They have offices in Italy, UK, South Korea, Australia, and North America. I've been to North America a few times, and it's a beautiful continent. So the tools that we will talk about here are the Galileo EMT suite from IDS, which is really an evolution of their platform, but it is based on some tools that have been around for a very long time. And then I'll also be talking about the EMA 3D suite, and again, it also has a code base that goes back to 1980. So again, everything that I'm talking about here is related to these two codes, but it's what we are talking about may not be specific to these codes in that you may do it with another platform. In any case, we're here to help. If you have questions, we can do training, whatever your tools you're using. Again, I mentioned these codes that I'm talking about today are robust codes in that they've been around for a very long time. And the reason that we use them is because they have a validation heritage, meaning we can match the simulation to experiment on a real aerospace platform and get a good correlation with simulation and testing. So another, I guess, differentiation that these tools and we as these two companies have is we have kind of a concierge model of simulation and test support, meaning that it's not a ticket, but you're going to get live same-day responses directly to your questions. We'll get on the phone, we'll fire up a WebEx session, we'll come out, whatever we need to do to solve those problems. And then, of course, as I mentioned, the big difference for us is we have a consulting team standing by, so we can be part of your EMC E3 team, or we can help you whenever you're in crunch times. And the last point, but not an insignificant one, is the tools I'm talking about are really low cost compared to alternatives. And I think for practical day-to-day items, they're really what you need. And finally, we could do integrations into your workflow, whatever tools you're using. If you have something that you want to add in terms of a capability, we can do custom integrations there. So I'm going to stop talking about that. I'm going to start talking about the topic of this webinar today. So first, we're going to go into details about why we would want to model cable harnesses in maybe a different way than is traditionally done, and talk about the real pain point of cables. So anyone who has spent any time modeling cables, I think will sympathize with the pain that I'm talking about that you have to go through with real cables. We'll talk about some automatic processing. Of course, in the world of computational geometry, 3D PLM rules the world. There's a 3D CAD for everything through the life cycle of most products. So tapping into that CAD and adding some automated processes, that's a huge time saver. The next thing is, how do you get things that are not well managed in that 3D PLM, namely those cable harness parameters, into the model? So we'll talk about some tools to streamline that process. And then we're going to talk about a topic that anybody who's had to deal with antennas who isn't the antenna designer, perhaps the integrator or the EMC guy, you know what this feels like when you have to deal with an antenna, but you do not know the complete information of the antenna, and then you're trying to do engineering on that antenna with a solution that's created for an antenna designer. So instead of that, we're going to talk about an EMC way to do it that is much faster and possibly the only way to get it done with incomplete information. And then we're going to talk about power balance method. So just like some of the automated CAD processes, the power balance is really a wow moment where you say, really, that's all I need. It's incredibly fast, and it goes to such a high frequency. Using statistics is really a revelation for how to deal with certain cases in EMC. And so taken together, I think if you can handle the cables well, if you know how to model your antennas easily, and then you can look at coupling between cavities, that's maybe not everything, but it's got to be 99% of EMC workflow. So what we're talking about here is most of everything that people will need in their day-to-day E3 EMC activities. So first we're going to talk about the cable harnesses and why that matters, why we would want to do something different than we've done in the past. So our specimen today, the platform that we're going to be looking at is this gentleman. Even though we're going to talk about an aircraft, these procedures that I talk about are really general for EMC E3. We could say the same tasks need to be performed on a satellite. It could be a tank. It could be a car with a radar on it, as they're wont to do these days. Or it could be a device itself, an electronics device for consumers or military space applications. A lot of the things I'm talking about today are very generic things, but we need some specimen to talk about. So we picked this beautiful aircraft to be our test bed today. So then the question is, what's the problem? Okay, so a long time ago, since the beginning of time, and it still happens today, you will see people trying to model an aircraft bay on the right using a simulation model that looks like it does on the left. Well, what's wrong with that? Well, just by looking at, you know, and in your EM intuition, in your gut, you know that you're not going to get the same answer from these two. Obviously, those cable harnesses, that bay has a huge fill factor. By that I mean you're going to have greatly more losses from fields in there. The cables are going to branch, so you're going to break up resonances. The critical point here is if you use the simulation on the left and then you do a test on the one on the right, you are not going to be off a little bit. You're going to be off by 40 dB, and that's enough to lose credibility with your managers. It's enough to and heaven forbid they did take someone seriously that modeled it on the left, because then they would over-harden their aircraft and would be heavy and hard to fly. So that's the real problem that we're up against here. But okay, great, we need to put all those complicated details of the cables. It's easy to say, you know, we have the CAD, we have all those details, but in practice it's not so easy. So yes, we're doing this in the computer these days. We have the 3D CAD. We don't have to wait for real aircraft, but we have to deal with the CAD. We have probably saved money because we don't have to build that aircraft to test. We've saved schedule, but we have added quite a bit of cost, because you're going to have an engineer somehow go ahead and simplify this. There is not any simulation tool I know of that can handle the 3D drawings like this and know what to do with the pins inside, that can understand the individual shields and the interactions there and get the right answer. This is just not the right information. And further, all those details, these days, they don't actually exist in the CAD. So if you open up CATIA, you're going to see these bundles like this that represent the cable routes, but it doesn't necessarily know the cable wiring diagram. It doesn't know how many pins are in each bundle. It doesn't know how it branches. It doesn't know about the shields. And that information is starting to get into 3D CAD, but it's kind of in an ad hoc way, not necessarily what is needed for simulation. So that's the main problem. This is labor intensive to get this model worked through. But the problem is we can't get the right answer if we don't include that complexity. So first I'm going to show an example where we've simplified a complex cable like this to just be a single bundle, and then another case where we do the same thing with simplifying the bundle but at a higher frequency environment. So let's talk about lightning. So this was published in the 2015 Lightning Conference in Toulouse, beautiful France. And so what we're talking about here, this is a real aircraft. So this is an aircraft, and the effort that went in here eventually was part of their basis for type certification. So this is not an imaginary example. This is a real world example. So you can see in this case, we have a real aerospace cable on the CAD that winds its way through the aircraft. So as a first cut, it was modeled as just a blob. So we said, okay, we'll make sure we get the right resistance and we'll match up the diameter, but we won't worry about what's packed inside. Problem with that, when we did a test to compare, we found that it was off by 9 dB. And 9 dB for lightning, it's kind of a lot. So we went back and we said, let's put in the real details with a transmission line model co-simulation. So when we put in the real cable harnesses, looked at the real branching, looked at the pins, the shielding, now we're able to predict with pretty good accuracy. You can see the peak is basically nailed and the waveform is just barely off. So this is a really great comparison. So we need some of those interior details of the cables to get the answer right. And it's not just for lightning. In fact, the situation is much worse for higher frequency environments. So HERF, RF coupling the cables, all of those type of environments. So this was presented at Euro-EM, again, beautiful France. So we see a similar topology where we model first with a uniform cable and then another one where we include branching, and the results are shocking. So we go from a 500 milliamps per incident E-field unit down to 30. So that's a lot. So, okay, we can say that's 24 dB, put it on a log scale and just say RF is hard, but that's not good. No one, if you put this on your homework and you gave the answer as 30 when the right answer is 500 or vice versa, you're not going to get a good grade. And we as a E3 EMC community can't get away with doing this. So, of course, the wave shape is very different. The quality factor is very different. And then some of those resonances are broken when we have the branch cable. So we could think deeply about the electromagnetic reasons about why we're breaking some of those resonances and changing the Q, but we don't have to. I mean, you can look at the cavity in that first picture and you know in your heart that you're not going to get the same coupling to the real cables versus that perfect line. It's just very intuitively obvious. So then the next question is, okay, so do we need to be accurate? Why do we care? So often for EMC and E3, it's very painful to over-specify your requirements from a simulation. So lightning suppression adds math. There's no way around it. So let's suppose that it's newly developed equipment. You're going to have to put TVS diodes, one on each line that you're dealing with, maybe down to ground, maybe across the differential lines. So that means for every pair you have, you may add up to 3 diodes. So that you have to find space for that on the board. It's not easy. And heaven forbid, everything today is commercial off the shelf. You're going to have to make a metal aircraft certify to, or a composite aircraft certify with equipment that was made for metal aircraft. So you're going to have to put in a filter box, and that box itself is going to add 10 pounds of mass. So that's not necessarily an ideal approach either. But it's not just lightning. So RF coupling, if we poorly specify the transfer function, that's going to require new testing for COTS boxes. We may have to put new filters in or add cable shields, and that design cycle can add cost. It can add time to your program. So we need to be accurate. So here's a summary of the problem. So the CAD description of cables that we get is incredibly complex. Of course, it's complex in the real aircraft as well. Simplifying by hand takes a long time. It's just not practical. And if we just use straight lines for the cables, and ignore the branches and the interior details, that's too much simplification. We get the wrong answer. So what do we want to do? So we think the best solution is the following, and we'll go through these steps. And when you see it, you'll see it feels like magic if you've been through this pain. So the first thing we want to do is we want to automate the simplification of the CAD cables. We need to get them from something that is a 3D description to a 1D description. So we have a start and end point for all the lines. Then we need a way to specify the interior details of the cable quickly just by reading off the wiring diagram. So that allows the E3 person to quickly connect that wiring diagram that's probably a PDF to something that we have in CAD simulation software. So we streamline that flow, so something that takes weeks you can do in one day. And then finally, we can use transmission line modeling that co-simulates with the 3D modeling, and that transmission line for the cables need to have all the branches, the shields, the conductors. And it's at this point, once we pack the cables with all the details, that we resolve that diameter that we simplified away in that first step. And in fact, that's reasonable because those CAD tubes that you see in the models, they're not real most of the time. They get put in early in the program. EWIS is the last thing that's typically designed. So those diameters from the CAD aren't realistic. So we actually have a better diameter estimate by packing based on the wiring diagram and then just using geometry to tell us exactly what the diameter of the cable should be. And then finally, a secret trick everybody knows about in simulation is we have to use acceleration methods, asymptotic solutions, or parallelization to speed up the calculation so that we can get through a large system. No one wants to use just one core of your laptop. If you can get away with it, you need either an acceleration method or parallelization or a combination of the two. Okay, now we're going to talk about some of the really cool stuff is how we do that automatic CAD processing. So we're going to first, let's look at our example aircraft. So the trick here is we have to deal with the structures first. So even though we're talking about cables, if we don't get the structures right, we won't get the right answer. So this is set up really easily. You just select the two adjoining surfaces, and then the line between them, the interface, we specify that impedance. So that's going to be a resistance, capacitance, and inductance for that joint. And we don't have time today. In another webinar, we'll talk about a quick, easy way to measure that resistance. But once you've got it and once you specify it quickly, then suddenly you have something powerful. You can use this model of the aircraft for your lightning, for your HERF, for your antenna sighting. You can use it for your antenna performance. You can use this same model for EMI EMC. So yes, it is some work to take the CAD and determine the resistance to the seams, but you can use it many ways, and I think it's as streamlined at this point as it can be. There's no way we can get around doing those interfacial measurements. It's too hard to predict that, especially for composites. And the ability to just click the two boundary elements to specify that joint just by clicking, that's as simple as it can get. Then the next thing, we're talking about cables today, so let's look at our cables. So as you can imagine, there are thousands of cables in aircraft, so rather than going through each one and simplifying it from a 3D description into a 1D start, end, and routing, why not take advantage of computers and let the computers do that computational geometry rather than hiring a mechanical engineer or your EMC guy to do this. So what we're doing here happens automatically, so this is going to save you days of time. So of course you could do many cables at a time. So you can see the timeline here. It's just a few minutes. So I'm going to skip. Let's say you got a couple minutes to do all these cables, go get a cup of coffee. I fast forwarded a minute so things go a little faster for today, and you can see we're done. So now we've taken that 3D CAD of the cables and we've turned it into a one-dimensional description that we can do something with. So now we're going to plot those cables as their one-dimensional representation. They're labeled for you, so you don't have to do that. It knows where the branches are in the cable. All that hard work that E3 guys don't like to do mechanical engineering. If they wanted to spend all day munging the CAD, they would have been a mechanical engineer. They studied fields and waves. So let's let the computers do that hard work. And so you can see now we've got those lines. We're ready for the next step of our process. So next, now here's the hard part. We've got the cable lines. The computer did all the work. We have this PDF of the electrical wiring interconnect document. So what do we need to do? We need to figure out the diameter of all these individual lines. We need to make sure our branches are in there. They should be in there automatically. From the previous step, we've got to specify what the shields are, if there are any shields in the cable. We need tools that have a connection to 3D fields and currents. It's pretty typical. Most tools have that. This one that we're talking about now, EMA 3D, has mHarness that does that. We want something that gives us a quick translation from the wiring diagram so that we can quickly get what's going to be in the aircraft into our CAD model. And since it's in a PDF, that's the best way to do it. So this is a conundrum. In the old days, we have this wiring diagram. How do we build this simulation model? This could easily take weeks to build something that was accurate to get in there. but because we've felt that pain so many times for the last 20 years, we have streamlined it as much as we think is possible. So, of course, if more details start making it into CATIA Index, maybe we don't have to use PDFs for this in the future, but this is where we are today. And I think we've squeezed something down that takes weeks into something that can take a couple days now. So we call this the mHarness Wizard for this particular EMA 3D platform. So let's go through and let's imagine that I have in my left hand the PDF of the wiring diagram that tells me all the cables that are routed in this aircraft. I need to somehow get that into my 3D model. So this is the way to do it. So we just need to tell the wizard how many levels of shielding. So I just said 2 levels of shielding. That means we have TSP shields as well as overbraids. You might have only 1, you might have 0. Now it's just a question of clicking our mouse on the lines that were created before. We have to tell it the termination points. Obviously this is going to be a straight cable, but we could repeat this step for any of the branches. So if some of those take a right on that line that goes off to the right, we could do that, and we could put in the details for that line on that side. So next, we just tell it how many conductors, TSPs, quads, whatever, are inside this cable. So we've done the path for the overbraids. Now we're doing the path for the TSPs. And for the inner conductors inside those TSPs, we don't have to specify that. So we tell its path, and now we need to tell the wire gauge. And so here's the great part. You don't have to do this work. We have measured tons of cables to understand their transfer impedance. So we've got quads, triples, pairs, singles, coax. We've got lots of gauges. We've measured Glenair cables to get their transfer impedance, and we've also measured Alpha brand overbraid to get its transfer impedance. So this could be a measurement program that could take you weeks to do, assuming you're using kind of typical cables. You don't have to do any of it. At least it gets you a start for engineering. If you're using some strange cables, strange overbraid, you could do that measurement and just update it in the software. But if you're not sure, the values are preloaded. So having this cable database is a huge time saver. So in this case, first we did a quad, now we're doing a TSP. And so basically we're telling the software the routing is the same, but the conductor type is going to be different. So this case we're going to put maybe a power cable as a single line. For some reason, aircraft guys insist on returning through the structure. So I guess that's what we'll do today. We'll return power through the structure. We just put a 20 gauge wire, and then I think we'll do one more power feeder in our harness, and we'll be done. So it's a 16 gauge, and it's a it's a single. So again, we're going to return that current through the structure. And so now the question is, what do we have? We've done this just for one long segment of cable, but we could have done this for the whole interconnect diagram, all the branches, everything. In a day or two, you can get through the whole aircraft, something that would have taken us weeks before. And then the software automatically packs the cross-section of the cables. It gives you no overlaps. It's great. Of course, if you don't like what the software gives you, you can move it around with your mouse. If you think the real packing is going to be different, of course, nobody controls how cables are packed in their EWIS. So the best you can do is just kind of randomly pack them through, and we're good to go. Now we've completed our harness simulation. So it knows the diameter based on that packing. It knows the transfer impedance of all those segments. And so we're ready for the next step, which is the simulation portion. So at this point, what we're showing is a full wave simulation. We've cheated by using some numerical techniques. You could call it like an asymptotic solution, where we're gradually adjusting the permittivity in Maxwell's equations to speed things up. Of course, the same thing would happen for RF. You can use some asymptotic methods if appropriate, or parallelization to speed things up. Usually one of the two is required for a full aircraft. But anyway, you've got to simulate it. And then the next question is, okay, we did all of that. We simplified the cables a little bit. Did we simplify them too much? Are we accurate? Well, I'm going to say that this is accurate. So we've been using this, a variation, a much more painful version of this method for more than 25 years, starting in the MD90 got lightning certification just with simulation of this same type, of a very old-fashioned version of this kind of simulation. And this is from an aircraft that got type certification just a couple years ago. So you can see we were measuring real wing boxes with these type of cables in them, and we're comparing experiment to simulation. You can see the simulation values in the x-axis, experiments on the y, and we just follow along the line. So it's as accurate as you can imagine, given the complexity of all the interfaces in a real aircraft, the routing of the cables, all of those uncertainties, and we can really just nail the values and be predictive. And this one was published in ICOLSA in beautiful France, but I can tell you that there's many more validations that aren't published, and some of them are even better than this one. So it is accurate for HERF and lightning, and that's proven in the literature. And so our argument here is that we have simplified the cables to make our lives easier, but we didn't simplify them so much that we're not accurate anymore. So that's really the magic of this approach. Okay, so we talked about cables. Hopefully you understand ways that in just a few days, or less if it's a smaller project, you can understand all of your RF coupling the cables, all of your lightning coupling the cables. You can do EMI, EMC, or E3 virtually for cables, and it is orders of magnitude faster, less manpower before your EMC engineers that do not like to touch the CAD. They still have to touch the CAD, but it's minimized as much as possible. Next, we're going to talk about something else that to me is kind of one of those, aha, this seems like magic kind of things. How do you deal with antennas? So we've got to deal with antennas as E3, EMC, and also RF professionals working at the system level. We need to know what those near-field antenna levels are for EMC. We need to know what we're radiating to so we can know what couples to other systems, other antenna. We want to know our antenna-to-antenna coupling for antenna sighting purposes. We also want to do our antenna performance. We want to know its gain, directivity, input impedance, all of those antenna performance parameters. And of course, it's up to us as the EMC RF at the integrator level. We've got to optimize this for our platform. So we've got to do several cycles of this. But keep in mind that whenever you're doing antennas, we need to do that optimization early in the program. You can't wait until you're in manufacturing and move the antenna. It changes too many things. We need to do that optimization very early in our schedule for that to be practical. But we don't have all the information that we need to do our job yet. Early in the program, we know we're going to get antennas from some supplier. We may not know which antenna. We may not know exactly what it's going to look like. This is an example of the typically provided information. So you can see not very much to go on given the complexities of what an antenna can do and all the coupling. So how do we go from this 3x4 table with almost no information to optimizing our design? Well, here's the trick. So keep in mind, we are not the antenna designer. You are probably an EMC or E3 group, or you're at an integrator, or you're integrating a consumer or transportation LRU device. You're not designing the antenna. So the question is, why would you use the same simulation tools into the antenna designer? It's nuts, because you wouldn't have all of the CAD, all of the port information available to you anyway. Some people do this, but it drives a lot of work, a lot of pain. So what we want to do is use an equivalent model that lets us build something that has an engineering representation of the antenna and what the antenna's affects without having to know all those details of the antenna that we may not know yet, may be proprietary. The supplier may not want to let go of that information. Okay, so how does this work? So we can make a really robust, reasonably accurate antenna model with very limited information. So we do that by one of several methods. We could force symmetry based on what we know about the antenna. We could use that pattern knowledge. If we know a style of antenna, we could force that symmetry. We can use interpolation to fill in those gaps using some pretty smart algorithms. We can use translate that to a spherical wave expansion method, or we could use equivalent far fields for aperture synthesis. So we create an aperture that gives us the equivalent far field, and then we can drive that on our platform. So, of course, this takes a little practice. So the generation of these models and checking their consistency is the most important part of it. But the good news is you're not alone. We're here, EMA IDS. We can do training on this. We can help you do this in a way that makes sense and learn to do this quickly. So the next thing, once you've got your antenna equivalent model, you can start your platform model. And again, you can inherit some of the simplified model from the other work. So you've got that existing platform, mesh it, put your antenna on, and now you can do that near field antenna levels for EMC. You can look at your antenna to antenna coupling. You can look at the antenna performance parameters, and you can optimize it. So we've gone from throw your hands up, I can't do anything, to with this limited bit of information, I can design my antennas and their co-located equipment to be compatible with each other and have pretty good confidence that when we put it all together, it's going to work. Okay, so antennas, there's a lot more to that. There's a lot of training we can talk about. We'll follow up with some more webinars, or you can reach out to us if you have questions about how to pull that off. But I want to talk about another thing that is power balance method. So this is a trick to do the coupling to cavities on vehicles or devices without having to do that brute force full wave simulation with a cluster of GPUs. We want something that can tell us using a statistical model, and really this feels like magic too, because how else do you do something like this? It's impossible to do, and suddenly you can do so much by thinking about the problem in a different way. So for full wave simulation, so we're limited by the number of cells in the problem space, and so that limits our memory or computational power. So there's always a trade-off between how small your mesh sizes can be and how much computational time that's going to take. Also the fact that you need smaller and smaller cells to get to higher and higher frequencies. So full wave modeling is not without its problems. So you would never see this if you go buy the $110,000 package for CEM simulation, and then you find out, oh, by the way, you can't do anything with this above 2 or 3 gigahertz for your platform, and you say, great, you know, what am I doing here? Well, maybe before deciding to brute force it, maybe we need to think about the problem in a different way. So what's the problem we're trying to solve? So for radiated emissions, radiated susceptibilities, we need to know essentially the shielding each of the cavities in our platform provide. And we know that's going to go up to 18 gigahertz. But if you have any antennas or systems that operate above 18 gigahertz, we have to go up to that particular frequency. So if your space platform, that may be in the 30 gigahertz range or even higher. But it's really hard to do CEM simulations above 2 gigahertz. Of course you can get there with a cluster, with the right tools, or you could focus on just a single frequency point. You can get there, but it's going to take, if you want to do RERS where you need all the frequencies, it's going to take a heroic effort, and it's going to get harder and harder as you go to higher and higher frequency. But the problem is that, you know, normally we would test this, but what do you do if you're early in your program and you don't have something to test? And of course, you want to optimize that design before you get late in your program. So it's really a conundrum. Of course, you know, testing can't be used in the design process unless you have some details from the previous version. This isn't acceptable today. We're expected as engineering on systems with PLM and our analysis tools to be able to figure out the requirements early. We can't wait for the prototyping stage. It wouldn't be accepted in Aero or any other discipline. It's not acceptable for EMI EMC. So how do we design it before we know? And the trick here is don't try to brute force it. Don't kill yourself. Approach the problem in a smarter way. Let's use statistics. So everybody knows about reverb chambers and using statistical electromagnetics for testing and the revolution that that's done for being able to assess multiple frequencies and multiple incident angles at one time in a reverb chamber. Well, in the discipline of working up the theoretical framework behind how some of those statistical electromagnetics work, we have the power balance method, which is a tool for us to assess the fields inside of cavities based on not the full geometry, but understanding a balance of power. So this is how it works. This is how the software module works. So the magical thing is we get the full analysis of the vehicle in seconds, not hours, not on a giant cluster. This is on your laptop. So the usual way that we approach the problem, we skip it. We don't worry about the full model of the vehicle, satellite, aircraft. We just want specific information. It's a topological model. So what we're going to do is we're going to look at the platform, we're going to look at each cavity, and we're going to look at what apertures that cavity has. And we're going to look at the losses in each cavity from absorbers and re-radiation out other apertures. We're going to look at all the different ways that the energy can couple in and out of that region. And we will do that for the entire platform. So we're going to look at losses, power leakage to the aperture, and the received power of the internal units. And so what we get is something that looks not like a typical CAD-based model, but a flowchart. So what we get out of it is we get the E field and the power statistical distribution. We get the non-stirred conditions in the near field regions of the source. We understand our interference margin, meaning we know this device will be upset at this field, and we know this is the field incident in the cavity, so what's our safety margin? We know the incoming power at each aperture, and we know the Q factor for each loss mechanism. So to get these individual details takes a little work, and you may have to do some very simple submodels to characterize the aperture losses as a function of frequency, to look at the losses of materials that are inside there. But compared to the work of a heroic brute force simulation of full wave, it's very easy. It doesn't take very long. And you can see it's been validated. So ESA spent some time on one of their satellites and working with IDS, and they found good correlation. So we can also correlate this to full wave methods. So we can compare what we get out of a full wave method at 6 gigahertz. It's kind of a crossover frequency here. So as you imagine, if we illuminate with 6 gigahertz, we get a wild distribution of fields on the inside of that cockpit cavity. And then we can compare what we get. So you can see the blue line is the full wave result. Of course, this is for a different talk, but you can't take that raw simulation result because that's not the same thing that people are measuring for HERF. It has to be averaged and decimated just like the network analyzer would. So the averaging, 2 different types of averaging are shown, the full averaging in the 97.5 percentile. So you can see the jagged red curve gives the EMA 3D results, and then you can see how that stays right within the mean in the 97.5 percentile of OCT. So given that for HERF, we know from studies from NIST that the overall uncertainty of those measurements is, a handful of dB, you can see using OCT in a simulation that takes seconds or minutes, not hours, we can do what would take us in full wave days and HPC clusters to get the same level of fidelity. So we can expand the RERS result up to 40 gigahertz. Again, it's an instantaneous calculation time, and we can use very targeted simulations to get our aperture cross sections and our power in the cavities, and we really extend our EMC E3 capabilities to things that we weren't able to provide any predictive engineering toward in a cost-effective way. Okay, so that's the end. I thank everyone for taking their time here because I know everyone is busy. We will have some questions coming up. Again, we talked about some interesting tricks for modeling cable harnesses that bring the time for that simulation down from weeks of man-hours to maybe a few days, targeted days. We've got ways to model antennas when we have the incomplete information that we always get on every project. And we've got ways to do the field coupling to cavities, again, with incomplete information up to frequencies that you can't get to otherwise. So I hope you see the details of a modern, I guess, thoughtful and economical way to approach EMC that is, for me at least, seems like a dramatic change, just a magical difference compared to the hard work of what we had to do before. So again, let me pause and we will open up for questions now.
Hi. Can you hear me okay?
Yes.
Hello? So the question that came up is, the use of extensive cabling systems like those you described seems to be a bit dated. Is there any movement toward systems that utilize daisy chain data distribution sensors, actuators, or RF systems in lieu of data off?
Sure. So what we were showing there is a particular fixed wing aircraft example. So that type of cabling that I showed is still in use. I could tell you firsthand that's what the cabling actually looks like. But certainly the approach of using transfer impedance is generic, so it works on other types of cables. And of course, coax systems would also use the same transfer impedance approach. Do you have anything else to add to that, Jen?
No, I don't think so.
Any other questions, Jen?
Okay, another question that came up is, can we simplify the antenna coupling model on an aircraft?
Yeah, so that simplifying the antenna coupling on the aircraft is kind of the point of what we're trying to do. So the old-fashioned way of doing it is you get a real CAD-based antenna model and you put that on the platform. So the way that traditionally has been solved is you go to the supplier and you say, give me your antenna CAD, and they say no, or so you make something up. Some software give you kind of a collection of generic antennas, and so you pick the one that you think looks most like your antenna and you put it on there. And then you come up with an antenna model. It takes a long time, and you have to do your platform model. What we're talking about here is, rather than doing that, you don't have your antenna CAD, which is a typical situation. You never have complete information. So these are tools that you take what information you do have, and you can, using a handful of methods, create an antenna model that either uses Huygens surface currents or other spherical wave expansions, or you can create an array antenna that mimics the same far field as the antenna pattern that you're given. And so you put that in, and all of that's automated. So unfortunately, I didn't have a video of that to show today, but we can circle back and talk about how we've simplified that step. And of course, there are other, many of the surface simplification and CAD cleaning steps we haven't covered in this session today, but we'll circle back and talk about them. There's a lot of ways to have numerical computational geometry simplify your surfaces for you.
I think that was the last question.
Okay, thanks for being on, everyone. Again, let me put the contact information up. In case you want to get a hold of me, Tim at EMA3D.com, I can connect you to any of the other co-authors at EMA or IDS, and thanks for your time.